Hello students. So today we'll discuss on a chapter, Arithmetic of Integers. It is a chapter of Advanced Mathematics book of SEVA. So let's begin. So when you come across the term arithmetic, it basically refers to working with numbers by carrying out addition, subtraction, division or multiplication on them. So we will carry out the arithmetic operations on these numbers, okay? And I guess you know the what are integers. So for your information, integers are real numbers and they can be written without any fractional component. So if I have to write the set of integers, it is basically represented by Z, okay, and it contains number 0, plus 1, minus 1, plus 2, minus 2, plus 3, minus 3. So these numbers. So if I ask you if 5 by 2 is an integer, so it is not an integer. It is a fraction. Okay. So it is not an integer. So example of integers for your more convenience, 0. We can write plus 1 or minus 1, then plus 2, minus 2. So these are integers. So you can write plus 100, okay, and minus 100. So these are integers, okay. So in this chapter we will basically deal with some elementary properties of natural number and their applications, okay. So we'll discuss the properties of natural number and we'll see how these properties are applied in various formulas, etc. Okay. So now what are natural numbers? So natural numbers are integers. They are basically integers, and it starts from 1. Okay, it's the lowest. If I ask what is the lowest natural number, it is 1. Okay, it starts from 1 and 2, 3, 4, and they are actually the positive integers starting from 1. Okay. Next, we will discuss two important properties of natural number. The first one is well-ordering property of natural number. Okay, so what is the well-ordering property of natural number? So we know that when we talk about the set of natural number, when we talk about the collection of natural number, we will always start from 1. We will always begin from 1. We will know that 1 is the least natural number. Okay, 1, then 2, then 3, then 4. We always know that 1 is smaller than 2, 2 is smaller than 3, 3 is smaller than 4. So when we write the natural numbers, we always maintain a well-ordered structure. So this sequence that starting from the least number and going on increasing, okay, with the further higher numbers. So this well-ordered structure is maintained when we write the set of natural numbers, and this property of writing the natural number in a well-ordered structure is simply the property of well-ordering of natural number. And we must point out this, that in every set, whether it be a natural number set or whether it be a any whole number set, we'll always find a least number. Like in whole number set, we will find it starts with 0, 1, 2, 3, 4, it goes on, and we know that for the whole number set, the least number is 0. Okay, so like that wise, the natural number set contains the least number, which is 1. So 1 is the least natural number. The second property is the method of induction. Okay, so when we consider the set of natural number 1 to 3 up to infinity, so when you consider a set of natural number, you have noticed, I guess, that you cannot say that this is the largest natural number. Okay, if you say that, let's consider 100. Okay, 100 is a natural number. So you will always find a natural number which is just next to it. If we consider 100, then 101 is the next natural number, which is 100 plus 1. Okay, if you consider, let's take 500 is a natural number. It is not the largest natural number. Then because you can find it, 500 plus 1, which is 501, is the next natural number. If you consider 1 lakh, then 1 lakh plus 1 is the next natural number. So we cannot say that this is the largest natural number. For every natural number, you will always find a number next to it which is greater than that number by 1. Okay, so this observation helps us to conclude that if we consider any natural number n, so the next natural number will be n plus 1. So this is a very important conclusion, and this will help us to prove many properties. Okay, so you must focus on this point, that if n is any natural number, if we consider any natural number n, then the next natural number, if I ask you which is the next natural number to n, you will always say that it is n plus 1. Okay, if I say if 26 is a natural number, then what is the next natural number? It is 26 plus 1, that is 27. Okay, so from the above two properties we can conclude two statements now. Okay, the statements are: 1 is a natural number. We know that 1 is the smallest natural number. It belongs to the natural number set. Okay, so 1 belongs to natural number and it is a natural number. So we know 1 is the least natural number. Okay, so this statement. And second statement is, for any natural number, if we consider any natural number, say k. Okay, k. If k is a natural number, then k plus 1 will also be a natural number. If k is a natural number, then k plus 1 will also be a natural number. So we get two important statements from the above two properties, that 1 is the least natural number. Okay, 1 is a natural number, 1 belongs to the natural number, and it is that is, we can say that 1 is a natural number. And if we consider any natural number k, then k plus 1 will also be a natural number. Okay, so these two important properties help us to obtain the set of natural number also, and we can define the natural number set with these two properties. Okay, so these are very two important properties, and we will use these two properties in obtaining various formulas. Okay, we will prove various formulas using these two properties. So now to get more essence of these two properties, so let's obtain the set of natural number, okay, using these two properties. So we know 1 is the least natural number, and it belongs to a set of natural number. So we wrote that 1 is a natural number. Okay, 1. So we are writing the set of natural numbers, and we first incorporated the element 1 in it. Okay, so second, we have this property that if k is a natural number, then k plus 1 will also be a natural number. So as 1 is a natural number, then the next natural number will be 1 plus 1, that is, which is equal to 2, right? Then if 2 is a natural number, then using this property, 2 plus 1 will also be a natural number, which is equal to 3. If 3 is a natural number, using this property, then 3 plus 1, which is equal to 4, will also be a natural number. Then we will apply this property through all the set, and we will obtain the set of natural number as 1, 2, 3, and 4, and so on. Okay, so this is how this property defines the set of natural number. So students, thus using these two statements above, we can establish the truthness of any statement involving natural numbers. Okay, so what is the meaning of it? We got the two statements that 1 is the least natural number, it belongs to a set of natural number, right? And if n is a natural number, then the next natural number is n plus 1. Okay, so using these two properties, we can prove or we can verify the truthness of any mathematical formula which involves natural number. We can prove a formula which involves a natural number, okay, using these two properties. Okay, so this is done by the method of induction, mathematical induction. So it states that let Sn be any statement. Sn, so the formula is defined as, we will name the formula as Sn, okay, where n is the natural number. Okay, so Sn be any statement which is made for any natural number n, such that S1 is true. That is, that formula is true for n is equal to 1. So when we put n is equal to 1 in that formula must be true. Okay, and secondly, we will consider that formula Sn is true for n is equal to k. So Sk is true. Okay, so we will consider that formula which is given to us is true for n is equal to k. Then if that formula is true for n is equal to k, then that formula must be true for n is equal to k plus 1. So the mathematical induction method for verifying a mathematical statement involving natural number states that if we define the formula, or if we define the statement as Sn, then that statement, if it is true for n is equal to 1, okay, and if we consider that it is true for n is equal to k, then it must be true for n is equal to k plus 1. So if we can prove these two rules, if we can prove these two statements, okay, then we will say that that formula is correct. If we can prove for any mathematical statement made for natural number that it is true for n is equal to 1, and it is true for n is equal to k plus 1, when we consider that n is equal to k is true, then this formula is true. Okay, then that formula is true. Okay, so we will you will get a better insight into this method if we consider an example. So we'll discuss an example. Okay, so let us consider this example. It says that using the method of induction, so that this formula is true, that is the sum of the natural numbers up to n, it gives n into n plus 1 divided by 2. It is true for all natural numbers. Okay, so we have to prove this formula using the method of mathematical induction. Okay, so let us first define this formula as Sn is equal to Snb 1 plus 2 plus 3 up to summation up to n, and it gives n into n plus 1 divided by 2. Okay, so we have defined this statement. Okay, so now from the method of mathematical induction, first we have to prove that this statement is true for n is equal to 1. Okay, now if we can prove that this statement is true for n is equal to 1, then we will proceed further and we will consider that let this statement be true for n is equal to k. Then if we consider that if this statement is true for n is equal to k, then we need to next prove that this statement is true for n is equal to k plus 1. And if we can prove that if this statement is true for n is equal to k plus 1, then this formula is true for all natural numbers. Okay, so let's begin. So let us first consider Sn1. Okay, so S1, that is, if we take S1, then LHS is equal to 1. So at first we consider the first property from mathematical induction, that for we'll verify whether this statement is true for n is equal to 1. So for n is equal to 1, S1, LHS, if you consider LHS is 1, the least natural number, you can omit this, and this is the first one. 1 is the natural for least natural number, and we get the LHS as 1. And for RHS, we put the value of 1 in this formula, 1 into 1 plus 1 divided by 2. So 1 to 2 divided by 2, the 2 cancel out, and we get 1 into 1 as 1. So we notice that LHS is 1, and we also got the RHS value to be 1. So we can say that LHS is equal to RHS. Thus Sn, the statement Sn, is true for n is equal to 1. So considering n is equal to 1, which is the least natural number, this statement Sn is true for n. So now we will consider the second property, which was let Sn be true for n is equal to k. So let us consider that Sn be true for n is equal to k. Okay, so if we consider that Sn is true for n is equal to k, then we can write that Sk is equal to 1 plus 2 plus 3 plus dot 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 up to k, gives k into k plus 1 divided by 2. So what we did is just in place of n we used k. Okay, what is the formula? If we consider it from the first step, so yes, it was this. So 1 plus 2 plus 3 plus dot 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 up to n gives n into n plus 1 divided by 2. So in place of n we just used what? We use k. Okay, in place of n we just use k. So fine. So let us consider that this is true. Okay, so let us consider this to be 1. Okay, So now, what according to second property, if this statement Sn is true for n is equal to k, then we need to prove that Sn is to prove Sn is true for n is equal to k plus 1. So we need to prove that Sn is true for n is equal to k plus 1. So mathematically that is Sk plus 1. So in place of n we use k plus 1 now. Okay, in place of n we use k plus 1. So 1 plus 2 plus 3 plus dot 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 up to k plus 1 is equal to, in place of n into n plus 1 divided by 2. This was a formula, right? In place of n we will now incorporate k plus 1. Okay, so n k plus 1, right? In place of n we use k plus 1, then again in place of n we will use k plus 1, then this plus 1 divided by 2. In place of n we have incorporated just k plus 1. Okay, so we need to prove this. Okay, so let us consider the LHS. Okay, what is the LHS? 1 plus 2 plus 3 plus dot 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 plus k plus 1. So in the next step we can write 1 plus 2 plus 3 plus dot 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 plus k plus 1. So you can think that why I incorporated the term k. So the k is actually within this summation. The k is within this summation. Okay, we have just revealed it. Okay, like 1 plus 2 plus 3 plus, which is the next number? It is 4. Then which is the next number? Plus 5. So it is within this summation, right? So likewise the k is within this summation. We can, it is if I ask that what is the smaller number, what is the next smaller number to k plus 1? The next smaller number to k plus 1 is k. Yes, so it was within this summation. We have just revealed it in this step. Okay, so we can write this, and I think you have the value of this summation. Yes, we have considered this to be true, right? From 1 we can insert the value of this summation. So what was the value? K into k plus 1 divided by 2. Okay, so we just insert the value of this summation from 1, and what is we are left out with? K plus 1. Okay, so we can write by 1. Okay, so in the next step we will simplify it more to get the result to be this. Okay, so let's begin with, next we can take the LCM, right? LCM, we can take the LCM 1 k. So we can take the LCM 2 into k plus 1 divided by 2. So we have just taken the LCM. Okay, so 2 into k plus 1 plus 2 k plus 1. So what we have done is just we have taken the LCM. Okay, so we can we see that k plus 1 is common in both the terms. So k plus 1 is common. Okay, so we here k plus 1 is common. We can make the k plus 1 like this, k plus 2. So we have just taken the k plus 1 common. Okay, so k plus 1 common. So what we are left out within the bracket? K plus 2. Okay, k plus 2. Now we know that we can express k plus 2 as, so we can express k plus 2 as k plus 1 plus 1, right? We can express k plus 2 as k plus 1 plus 1. And if we notice that this is nothing but this is the RHS. This is the RHS. Yes, just look at this. K plus 1, k plus 1, k plus 1 plus 1 divided by 2. So this is the RHS. So now we can tell that yes, Sn is true for n is equal to k plus 1. So we can now conclude it like this, that at first we considered that the statement, we checked for if the statement was true for n is equal to 1, which was the least natural number. So we found that this statement was true for the least natural number n is equal to 1. Then we checked, then we considered that it was true, the statement was true for n is equal to k. Okay, and using this we proved that this statement was true for n is equal to k plus 1, which was next natural number to k, right? So by these two properties now we can establish that the statement Sn, which is the summation of the natural numbers up to n, is equal to n into n plus 1 divided by 2. This statement is true for all natural numbers. So I guess it was helpful to you, and we shall continue the lecture Further, we will see more examples related to this topic. Thank you.